Okay, good afternoon, everybody. My name's Harry Natahis. I'm the president of the Vertical Flight Society East New England chapter. Welcome to our second attempt at a webinar. We had last month we did a webinar on the impact of COVID-19 to the rotorcraft industry, and got a lot of good feedback for our little sleepy little chapter here. And so we thought we would switch to this format for our next. Essentially what used to be our dinner meeting. We've now gone to sort of a lunchtime webinar. And so I welcome you to this webinar. I would say if you're not a member of the Vertical Flight Society, please consider joining. It's a great technical society, and it is primarily a technical society. You get to exchange ideas with like-minded people in your industry. You get a subscription to Vertiflight, which is a great industry magazine, and you get a whole bunch of other benefits that are just really terrific benefits that will help you progress in your career in vertical flight. I would like to give a shout out to the Vertical Flight Society headquarters, and in particular Jim Sherman, who's helped us and allowed us to use this webinar software. And so thank you, Jim, for hooking us up with the software and teaching us how to use it. I'd also like to thank our sponsor for this month, and that would be FLIR Systems and Peter Smart. And FLIR Systems has been a great sponsor of our East New England chapter, and we thank you again, Peter, for sponsoring this webinar with the bronze sponsorship with FLIR. Just real quick, in terms of the webinar mechanics, we've got, it takes a village to run these things. So we have 3 people behind the scenes that work with us. Lauren Charlinger is working the mechanics of the slides and the videos, and Scott Hanula is going to handle the question and answer for us. So if you have a question during the webinar, use the question feature on your menu to ask that question. You can put the question in anytime, so when you think of it, just type it in, and Scott will consolidate the questions and ask the questions on your behalf after Peter finishes his talk. And so now I will introduce Peter Schmidt. So Peter, welcome, and thank you for agreeing to this new format for us. And we had Peter lined up for the March webinar, the March dinner meeting for the East New England chapter, and obviously we had to cancel that due to COVID-19, and we're kind of waiting to see how this thing was going to play out, and it does appear that this is the new normal. And so at least for the foreseeable future, we'll be doing these webinars instead of our dinner meetings. And so Peter, thanks again for agreeing to join. So Peter is with Transcend Air. He was a co-founder of Transcend Air in 2017 with Gregory Bruel, who formerly led the Silicon Valley-based eVTOL company Electron. Peter Schmidt is a senior technology advisor for air taxi company Linear Air, which was Transcend Air is headquartered in the greater Boston area. Transcend's VY400 is a tilt-wing VTOL aircraft designed to provide VIP and city-to-city transport with exceptional performance at half the operating cost. The company is currently seeking a manufacturer to build and fly the full-scale prototype of the VY400 air taxi. So there's an opportunity there. And now about our speaker, Peter Schmidt is co-founder and chief operating officer of Transcend Air. Is an entrepreneur and executive with startup turnaround experience and large enterprise experience. Peter's aviation roles have included test pilot, president and CEO of Linear Air, an Eclipse 500 operator, and Part 135 online charter marketplace. COO of Jet Advisors, a business aviation consultancy. Senior vice president of National Aviation Academy, the second largest Part 147 aviation mechanic program in the United States. And in his pre-aviation career, he led several networking and embedded systems companies, including a chief technology officer of North America for Ipanema Technologies, and CEO of Echo Engineering, division manager of Teradyne, and co-founder and president of Midnight Networks. Also an aerobatic pilot. Maybe that could be the source of another webinar, Peter. So that is, I'm sure, of interest to a lot of our audience. He did his undergrad in computer science and master's degree in management at MIT. So Peter, certainly appreciate you agreeing to host the webinar, and I look forward to your presentation.
Well, Harry, thank you. It's been a real pleasure already. Thank you for that wonderful introduction. Shout out to Fleer for supporting this. I'm sorry I don't get to have dinner at a nice Italian restaurant, but it's fun to be able to reach perhaps a wider audience this way. So yeah, there's several things in my intro that I think are extremely relevant to today's talk. I think my presentation today may be a bit different than the audience is used to, but it's illustrative of the journey we've taken to get to where we are with the VI 400. And naming it VI, it was sort of coincidental that it's also VY, as in the speed to gain altitude fastest. But we actually came up with VI 400 because our ultimate goal is to make that a verb, so that you will VI down to New York, or you'll VI from San Francisco to New York someday. We're not there yet, but today's presentation, I think, will give everybody a good idea of where we came from and how we're planning to get there. So as you can see on this cover slide, this is the VI 400R. R stands for Reserved Edition. It also stands for Racing Inspired. And it is the model of our aircraft that is designed for VIP transport. And I'm going to focus on how VIP transport is the linchpin of our strategy for getting this aircraft into 2 and possibly 3 markets, and how we think about that. So let me see if I can advance slides here. There we go. So the Reserved Edition VI 400R is meant to be a bespoke, in other words, customized to the customer's specific desires, luxury tilt wing VTOL aircraft. VTOL, of course, is vertical takeoff and landing. And we'll get into all sorts of why those details matter. But I want to kick this off with a brief video to introduce everyone to the VI 400R. So let me run that video for us here. I'm told you GE folks may have to get through some permissions in order to play this. So if that causes you to miss some of the video, maybe we'll end up showing it again at the end. So let's give this a try. That gives you an idea of what we're shooting for. Those were obviously some very pretty renders we've put together. And as you'll see, we're not just pretty renders. So that's where we're going to. So the question is, where are we coming from and why? And that's really what I want to address in this talk. So the next, I'm going to show you another video. This is the Canadair CL-84 tilt wing VTOL for 1968. If you're not familiar with the CL-84 program, it was quite successful. They made an aircraft that was not just VTOL, but also short takeoff and landing, conventional takeoff and landing. And in fact, it perhaps was a little bit too versatile for its own good. But I wanted to show you its flight dynamics because this is a big inspiration for our aircraft and our program. So I'm going to play another video of the CL-84. Let's see, 1 second. There we go.
With the wing tilted up, the power lever is advanced to make a vertical ascent to hover. As in all modes of flight, the aircraft is controlled by the stick, rudder pedals, and power lever.
Actually, let me pause that because I'm sharing that off my screen and I need to actually share it off of the webinar platform. So do over.
With the wing tilted up, the power lever is advanced to make a vertical ascent to hover. As in all modes of flight, the aircraft is controlled by the stick, rudder pedals, and power lever. To fly sideways, the stick is moved sideways to command differential propeller pitch instead of ailerons, as in conventional flight. The 84 can fly sideways up to 35 knots. To rotate the aircraft, rudder pedal movement controls the flap ailerons, which, being immersed in the slipstream, provide the necessary yawing moments. This transfer of control authority is obtained by means of a mechanical mixing box in the control circuit containing a series of cams which rotate with wing tilt. In this way, a given control input is translated to a command to the relevant control function. A thumb switch on the power lever selects wing tilt angle. Here the wing is tilted beyond the vertical to put the aircraft into reverse flight while the fuselage remains level. The 84 can fly backwards at up to 35 knots. The ability of the aircraft to fly sideways and backwards is a measure of its ability to perform hover turns in a wind while remaining on station and handle crosswinds during takeoffs, transitions, and landings. 0 to 100 knots takes about 8 seconds. The flying demonstration concludes with an inbound transition to a hover landing. The relative movement of the horizontal stabilizer with the tilting wing is clearly seen. A small reduction of power is required to complete the landing as the aircraft enters ground effect.
All right, so that gives you a taste of the CL-84 and how capable it was. So let me go back to the slides here. So when we started this program, we've been working on this one way or another. Well, parts of it date back to 2009, so over a decade already. I got involved in 2013 and started consulting to Greg informally, and then quit my day job in 2016 and joined Greg and Oliver Garrow at Elytron Aircraft, which we then branched off from with launching Transcend Air and the VI design. So the question that Greg started to ask himself back prior to joining Oliver in 2013 is what makes for a successful aircraft program? Because the passion that we have behind this is such that we want to see this aircraft make it to market. We want to see it revolutionize the world of regional transportation. And so we did a lot of time pondering this question. And this literally was our entree into this program. So the answer we came up with is demand. Lots and lots of demand. That's what you need for a successful aircraft program. Because getting an aircraft to market is expensive. If you want to have a return on investment, you want to sell a lot of aircraft. It's that simple. So that demand also has to be real, not imagined. As Harry said in my introduction, I made the transition into aviation as a professional, not just a weekend aerobatic pilot, in something of a turnaround situation with Linear Air, the Part 135 operator of Eclipse 500 very light jets. For those of you who've been around the industry since the early 2000s, you probably remember the giant hype bubble around very light jets. And the idea was if you could make twin jets that cost under $1 million, there was this huge pent-up demand at regional airports where people would walk up, get in the aircraft, and fly wherever they wanted to go. The problem with that is, as I learned the hard way, that's not real demand. There is not a huge pool of pent-up demand in small regional airports, fundamentally because there aren't very many people there, and the people who are there don't tend to travel that much. So it sounded like a good idea. I was persuaded by it. It took me 5 years of working to try and increase sales at Linear Air to come to the conclusion that that's not what the deal was. So sadly, as we were researching this whole question around what makes a successful aircraft program, we learned that most aircraft that can be built won't be built. I think we're all familiar as aviation enthusiasts with cool aircraft that we see displayed at Oshkosh that never make it to market, or these cool home builds and kits where there are only 10 or 12 made by anybody. And sorry for the hand gesture, it's to get my camera white balance back so I don't look all orange. So most aircraft that can be built won't be built. So because, you know, beyond, even if there is a lot of demand for something, if you're going to meet it with a commercial aircraft and not a home built, you need a design that can meet it while being certifiable without excessive cost, certifiable without excessive risk, certifiable in a time frame that enables a competitive ROI, return on investment. It has to be manufacturable at a more than competitive profit, or why would anybody build it? There'd be something more profitable to build. It needs to be operable at a more than competitive profit for commercial operators, or cost for private owners, or again, why would anybody want it? And given this is aviation and we're going to the bother of certifying something, you want it to be upgradable as needed for the foreseeable future, which, you know, in our case is 20 to 40 years. It's hard. It's really hard. So we literally spent years refining designs and looking at economic models before we launched really full-time into Transcend. Because there's another problem. Most aircraft that are certified end up profiting somebody else, if at all, if they make a profit at all. Because if you want to apply new technology, that new technology takes time and effort to get right. And that extra time and that extra effort pushes back against all of these bullet points. You know, extra time harms the ROI, the return on investment. It adds risk, which is going to add cost. Getting it right, even if it someday may be cost advantageous, usually requires upfront investment that hits the profits. And then all of that results in a more expensive aircraft than you want. And that pushes back on operable at a more than competitive profit or cost. So, you know, there are lots of examples of this, sadly, but I'm very familiar with the Eclipse 500, and that's a perfect example. You know, they were betting on new manufacturing technology, new avionics technology, and flight control systems, and new engines. And of those, the new engines didn't work at all. The new avionics technology took a decade to get to the promised level. You know, the manufacturing technology worked, so that was a win. But, you know, the Eclipse 500 ended up only shipping about 260 airframes. And I think the entire certification by the time they were done was well over $1 billion. So, and those 260, most were sold at $3 million, not under $1 million. And of course, the original Eclipse went bankrupt and was bought out of bankruptcy. So, you know, it's a poster child for the challenges you face when you want to bring a new aircraft to market. So the big question to us is, what if you don't want to go bankrupt and let someone else make all the money off your aircraft? And here's our answer. Target already proven markets with a high TRL design. That's not to say we're not innovative. We're innovating in other ways about how we approach the program. But innovation that makes the certification riskier and take longer, if you don't have to do that, it's better not to, and we don't have to. So we've designed an aircraft that's going to fill two proven market needs for VIP transport as a helicopter replacement and as a regional airline. It's going to be manufacturable and certifiable. Part 23 rewrite helps with that, of course. It'll be profitable for the manufacturer, very profitable. Profitable for the operator. That's where I come from. We literally have designed this aircraft from the standpoint of being profitable for an operator. Needs to be liked and trusted by passengers, and I hope that what you saw in the intro video will help make it clear that people are really going to love flying in this aircraft. And it needs to enable lower prices for both the aircraft and for any fares you want to charge on it, right? If you want to have lots of demand, it's not enough to just be better, you also have to be cheaper. One of Greg's key insights that he brought to this, in fact, it's part of why he reached out to me originally to discuss this VTOL concept, was his point that it's a mistake to bet your success on future technology developed by someone else, right? We saw that with the Eclipse, they depended on the Williams engine. That didn't pan out, and that was a huge disaster. You also saw it with Dayjet. Eclipse had a huge order book from another startup, Dayjet, that thought that route optimization algorithms would be enough for them to win a market, and that didn't pan out either. So we've focused on trying to have a design that's buildable and certifiable now. You know, my own lesson I've hinted at, as I said, I spent 5 years at Linear Air working with the team to try and market more trips on the Eclipse jet. And we succeeded to a certain level, but not to a mass market level. That's where I came away with the religion that you need to make something that's both better and cheaper. That's how you win. And we see that in high tech. Moore's law, the exponential improvement in computer processing power and cost has driven cheaper, better, cheaper, better. Aviation doesn't benefit from that directly. The physics of aluminum, air, jet fuel, and batteries doesn't change. Chemistry for batteries is changing, and that's a positive, which we'll get to later. But we're not betting on that now. But those things don't change. So we've had to benefit by applying aspects of Moore's law in other ways to be innovative and get where we are going. So why do we think the program will succeed? Well, the aircraft has 3 markets, and 2 of them are already proven markets. There's VIP helicopter disruption. People buy helicopters for VIP travel today, and that's about a $4.5 billion total addressable market that's annual. Regional airline service disruption. This is what actually really is we're most passionate about, but I'm not going to spend a lot of time on that today because we're talking about the VIP segment because it's the linchpin. And then as we've been out in the world promoting the aircraft, we've gotten interest for military applications. We really know nothing about that yet, but people smarter than us about that tell us that there's potential. So let's look at the ARS market. And it has lots and lots of demand all by itself. Forget military, forget our airline. Just selling this to replace helicopters for VIP transport is enough to meet all of those targets for a successful program. So why is that? Well, simple math. The aircraft is half the price of a medium twin, like a Sikorsky S-76D. It goes almost 3 times faster. It's actually, depending on what cruise speed you want to ascribe to the helicopter, it's somewhere between 2.5 to 3. And it has 1/4 the operating costs on a per mile basis. So that multiply that together, that's 24 times the value of a medium twin helicopter. And since you guys are all vertical helicopter, vertical flight nerds watching this, I assume, or almost everybody is, I'm actually going to go through this chart a little bit in detail. So the first thing I want to highlight is we've got prices here, and I'm showing a $5 million price for the VIP aircraft. That's with a custom bespoke interior, custom livery. Now, what do you get for $5 million? Well, you get a cruise speed of over 400 miles an hour, a range of up to 550 miles, and an interior volume of 252 cubic feet. So how does that compare to other aircraft in this list? Well, if you look at the interior volume of the S-76D, it's 243 cubic feet. So it actually has more volume than the S-76. The AW139 is 283. So it's not quite as much as the 139. But on the other hand, it's less than half as much. And it goes farther, and it goes 3 times faster. So somebody who wanted one of those helicopters might well decide that a buy is a much better choice. In fact, we're counting on that. If you look at the base prices for, now one of the things I haven't explicitly pointed out yet and need to bring up now, one of the keys to the cost savings and the certification, the certainty we feel about getting through certification comparatively, straightforwardly, is we've simplified the aircraft design, and a key part of that is that the VI is a single engine aircraft. It has 2 propellers, but it's 1 engine. So we're a single engine turbine powered aircraft like these helicopters on the left. So you've got a 407 GXP listing for 3.1 million, an H125 at 2.4 million. So the Vi's more expensive than that in bespoke luxury trim. But again, you're looking at 252 cubic feet and the payload and seats to match versus 84 cubic feet in the Bell and 61 cubic feet in the Airbus. So it's really a different class altogether. And in airliner trim, we actually expect the price on the Vi would be more like 3.5 million, which puts it right down. So a non-luxury variant puts it right down with the Airbus and the Bell. Now, if we look at how it compares to fixed wing turboprops, the thing that jumps out at us is range. And of course, there's no such thing as a free lunch in engineering. You have to make trades. And so the trades we've made are to disrupt the helicopter market and not have a product which I expect to be particularly interesting to fixed wing turboprop buyers, because they want to go 1,000 miles, 2,000 miles, and the Vi tops out at 550. It is faster than those turboprops. I'm looking forward to the day it's certified. It will immediately become the world's fastest helicopter and the world's fastest single engine civil turboprop, unless TBM ups their game between now and then. So 24x the value. That's why we're really excited. Last week, the Rob Report, a luxury publication, awarded us Best of the Best in Aviation in the category of VTOL concepts. And we were very grateful for that, very excited. Of course, we agree. And in that same set of awards, among other company like the Gulfstream G700 and the Embraer Air Praetor 600 was a helicopter. So the award to helicopter was Airbus's new Airbus Corporate Helicopters ACH-130 Aston Martin edition. And if you look at the two, I have the two pictures here from the award on the website. That Aston Martin interior is just beautiful. It is bespoke luxury worthy of the Aston Martin brand name. And we've tried to achieve similar levels with our design for the R model. I think we've done a decent job of competing so far. I also think this picture neatly highlights the advantage of the wing. So the wing on the Vi is part of what lets us have this giant cabin. So if you look at the legroom, if I put two 6-foot tall people in those chairs facing each other, they stretch their legs out, you can't even touch feet. Whereas, the ACH-130 has a traditional light helicopter cabin, and so you can sort of see the difference in the legroom. So again, we really are excited about the value that the VTOL tilt wing design is going to bring to this market, this VIP market. So that being said, what else can I give you some context about? Well, because the Vi looks like an Osprey, and people have heard horror stories about the Osprey, there's this urge to think, oh, this design is going to be very complex and expensive, but it's not. Our design targets were number one, simplicity, two, reliability, because we want this to be an airliner. So we're not looking at a GA aircraft flying 300 hours a year. We're looking at an airliner flying 2,500 hours a year. So it's got to be maintainable. Interoperability, and that has lots of things. But having jet fuel in it, we can fuel it up anywhere. There's existing infrastructure, there's existing fire codes, there's existing air traffic control laws. We don't need anything new. If we had this aircraft today, we could fly it today in the existing national airspace system with the existing fire codes, existing everything, and it just works. Affordability, well, if you look at the cost of these tilt rotors, which we characterize as complex and expensive, you've got two helicopter rotor heads sitting on top of engines that tilt, that are yoked together. My hat's off to Bell and Boeing, because they're wonders of engineering, and I think they're actually doing very well now. But you've got the Osprey at 71 million, you've got the V280 at somewhere between 30 and 50, as best I understand. The 609 coming in at 24 million, and an airliner trim, like I said, our aircraft should come out at about 3.5 million. And again, if I go back to this slide, there's no magic there. We're building a single engine turboprop with the same off-the-shelf technology that everybody else is using. And you can see the price point sort of falls in line with these other aircraft that are similar scales, similar appointments. So adaptability, we want the aircraft to be very useful to the owners. So we put features in there, one of which is all the seats are removable. And you may have noticed that there were big, fat, puffy, comfy chairs in the video, and there are also skinny, very lightweight chairs. So you can trade fuel for seating if you want to, and that's how we get extended range. And then upgradability. And I have to say that we are not an eVTOL to start, but we aspire to be an eVTOL someday. And so we've designed the aircraft to be upgradable at the depot, you know, in a repair station, to electric someday. So that the fleet will be upgradable to electric in the future, which I can talk about a little bit more. So I said we're not just cute, pretty renders, although those renders do come from our manufacturing CAD or design CAD stuff. We believe strongly in flying prototypes. You have to fly designs to see how they really do. And as I mentioned, our predecessor company, Electron Aircraft, Greg partnered with an inventor named Oliver Garrow. Oliver is one of the co-founders of the Sabre Wing. So he is still doing VTOL. And this is a sequence of prototypes that Oliver designed, built, and flew to learn about what works in VTOL and what doesn't. And we've continued that lineage into our aircraft, into the Vi-400. And so we have, since 2009, you know, our aircraft program benefits from over a decade of flying VTOL prototypes, 16 of them, and all but one were electric. So it's possible we've flown more different electric VTOL designs than anybody else at this point. We did put together, Oliver and Greg built a 2,000-pound manned prototype, which you see here, which is a tilt wing with a Prandtl wing, a box wing around it. And so we have experience with the benefits and limitations of electric. For our mission, we start out turbine mechanical, but we made it convertible later. We've been flying at the 5th scale now for a couple years, which we've used these 5th scale flying prototypes to validate various aspects of the design. One of the key attributes of our design is we're relying on a whole airframe parachute as one of the key safety elements of the overall safety system. And the subscale aircraft does have a parachute, not just to ape the big one, but for similar reasons. You know, this is a pretty big UAV. If it gets away from you, you want to be able to bring it down safely, and a parachute's a great way to do that. And we've also been using this to prototype our flight control system and continue to do so. So we'll be continuing to use this as a great platform. You know, 5th scale is effective, it gives you good data, but it's inexpensive to work with. And so this is one of those key technology innovations that's let us get as far as we have. You know, between what software has brought to our CAD design, to our simulation, to our analysis packages, to letting us build these kinds of prototypes cost effectively. That's really is what has let us operate as a skunkworks for these past several years and develop the design this far. So what we put before you is the Vi-400, is what we would say is a combination of proven technology that results in a disruptive aircraft. So a few more specs here. The aircraft's fast, 352 knots. It'll climb at 4,750 feet per minute, at max gross on a standard day from sea level in helicopter mode, and 8,500 feet per minute in airplane mode. So, you know, it's high performance, and the rate of climb is perhaps more important than the top cruise speed, because that rate of climb lets us get up and out of earshot very quickly. It's fuel efficient, so in a military context, it'll burn half the fuel per kilometer of an OH-58D Warrior, you know, the light scout helicopter that's about the same size. We've kept it very simple. What does that mean? Well, some of what it means is it doesn't have any hydraulics. It's going to be full fly-by-wire with electric actuation. It's a tilt wing, not a tilt rotor. So it has propellers, not rotors, no rotor heads, no cyclic, and it's a single turbine. And when you don't have redundancy, you don't have to design that mechanically, and you also don't have to teach your flight control system how to manage it, and you don't have the giant test matrix that results in certification from having to demonstrate that all of the failover cases and everything work. So that's a key aspect of this. Affordable, $3.5 million in airliner trim. Effective, so the autonomous K-MAX is a wonderful aircraft, and it delivered millions of pounds with no harm to troops on the ground. But it's a sling load aircraft, and so it flies slow. So it can carry 6,000 pounds at about 85 knots. Well, you know, the autonomous Vi concept that we're showing here can carry 2,000 pounds at 350 knots. And so it turns out when you run the numbers, it can put 133% of the cargo per hour onto the ground versus that K-Max. So there may be a use case for that. If you need to get a lot of material onto, say, a beachhead quickly, maybe that's a good choice. And then future-proof. So we're turbine mechanical to start. And you can see on the picture here, the turbine, you can see the parachute below it back here in the empennage. And the turbine feeds in a T gearbox, which goes out to our drive shafts and the wings. There are L gearboxes in themselves. And we've done extensive trade studies, and we were not able to convince ourselves that going electric in the drivetrain made sense. Every time we run the numbers, the mechanical drivetrain weighs less than a high-power electric drivetrain of the similar horsepower. So mechanical actually weighs less. We're like, okay, great. And of course, for our mission, going that fast, there's no way to do that right now except with a turbine. But in the future, you can see just underneath the turbine, underneath the wing, is our big central fuel tank. It's a helicopter-style bladder puncture-resistant fuel tank. The grand and glorious future, when electric energy density and volumetric efficiency gets there, we'll be able to take that fuel tank out, we'll be able to take that turbine out and replace them with batteries or fuel cells and big electric motors. And we'll drive the same electric drivetrain. So that's why I say we'll be able to upgrade these aircraft to electric, fielded aircraft to electric when we get there. And we don't necessarily have to wait to replicate the full mission envelope. It may make sense to start converting some aircraft before that for shorter hops, for example. So that's why we say it's future-proof against one of the obvious trends, which is electrification. In the meantime, we'll use sustainable alternative jet fuels and get off the ground literally that way. So there's lots more specs here. I'm looking at time. I think we're kind of doing okay. So let me just go over this layout. So you can see here the VIP R configuration. And so it is a 6-place aircraft. So we've got 4 club seats and then 2 seats in front. The aircraft's intended to be single pilot and single pilot IFR certified. So obviously the flight control system is going to have all envelope stability augmentation. We'll also have envelope protection. We're working on that now. We've achieved all envelope augmentation with our PC-based full-scale simulator, and we're working on envelope protection now. So someday it's possible. I mean, the plan, the roadmap is that pilot seat will get turned into a passenger seat, and it'll operate as an optionally piloted, remote piloted vehicle. So the technology is all going to be on board to facilitate that, but we're not planning to certify it that way. Our business case does not need that. We can make money with a human pilot, and we don't know when the regulators and when the market will accept a civil, optionally piloted, remote piloted vehicle. So we don't have to place that bet. So I'm happy about that. But when the tech gets there and when the acceptance is there, we can capitalize on it. And certainly the airline gets more profitable if you turn that into a revenue seat. Also, as we've heard from the Air Force with AFWERX and the orbs they're talking about, there's clearly a desire to be able to put non-pilots into the seats, to have them as aircraft operators as opposed to traditional old school pilots. This is a nascent idea. It's evolving. I'm not sure how good an idea it is yet myself, but we've designed the aircraft, again, for upgradability that would support that. And I can tell you right now, whether you're a pilot or not, I could teach you to fly our full-scale simulation in about 5 minutes, and you'll be able to take off, transition, cruise, transition, and land in the sim with no flight training at all. So, that as a result of the flight control systems algorithms. In fact, we can even program the aircraft's maneuvers now. And so that's clearly, obviously, the way of the future. So we're building the capability in. Some other points about the R specifically, I mentioned that the seats are removable. That's something that the Eclipse 500 has. It's not presenting that as a revolution, but what it does enable is it enables longer mission. So if we put the super light seats in there, take the comfy seats out, it adds significant, it could add 100 miles of range. And in fact, if you want to take all of the seats out, you can. So we expect our customers probably will buy sets of both seats for the aircraft, so they have that flexibility. We're targeting this to have a max takeoff weight of 6,990 pounds, so keep it under the 7,000 pound Part 27 limit. We are designing it to comply with Part 27 vertical crash worthiness, as well as obviously the Part 23 regulations. We expect this to be certified under a combination of Part 23, Part 27, and 2117B. We mentioned it's a single engine. We rely on the parachute as a primary way of safely delivering people to the ground in the event of a departure from controlled flight. The aircraft should auto-rotate as well. We're still refining that capability. So, you know, the Part 23 rewrite opens the door for us to point to the now 2 decades of Cirrus's success with a light piston single, where the parachute has proved superior in saving lives to relying on, you know, the heroics of a pilot dead sticking, you know, the aircraft in for a landing. So, you know, we're looking forward to going through that data and going through that process as part of our certification path. One of the things that's, as a former operator, this is something I really have to emphasize. It drove me crazy trying to operate light GA aircraft for money because their specs are choose one, right? The Eclipse jet can go 8,000 feet or whatever it is, it can go 600 miles an hour, it can go 1,000 miles, it has 6 seats. The problem is it's choose one of those. It can do all of those things, but it can only do them one at a time. If I wanted to put adults on that aircraft and fly them for revenue, I couldn't really put more than 3 adults on that aircraft with rollerboards. So, you know, that was leaving money on the table. So all these specs that I'm showing for the VI are at max gross, fully loaded, with 30-minute reserves. So helicopter IFR reserves. So we can put a 200-pound pilot, 5 200-pound passengers, and each of them can have 50 pounds of rollerboard and personal item on this aircraft. It will all fit, it will all be comfortable, and the aircraft will perform the way we're showing here at that point. You know, this is, as I said, it was a pet peeve of mine, and so it was a key driver behind the design here. Other key drivers come from Greg's experience. So tying back to why I started this story showing you pretty pictures and talking about what makes a successful aircraft program. Both of us come at this as not being airplane guys, right? Lots of aircraft are designed by people who went to Aero-Astro programs. You know, MIT has a very fine one. I didn't attend it, and I feel a little bit like the lost sheep now, working on aircraft design. But the thing about not being an Aero-Astro person is that we only designed this aircraft because we needed to exist to fulfill our vision for what the airline service can be. Greg wants that vision because he wants to be a passenger, and he wants his mother to be a passenger, so his mom can, you know, get on the aircraft and be comfortable and have it be an easy trip, unlike airlines today. I want this aircraft because I want an aircraft where you can get rid of all of the stuff that makes air travel really annoying, which is not so much the ride in the airplane, it's the getting into the airplane seat and getting out of it again. It's the traffic jams, it's the parking, it's the TSA, it's the line to board. That's what excited me about trying to make money with Eclipse jets, and now we've got designed aircraft where we can really do that. So we come at this as the customer and the operator, and we've designed the aircraft from the customer and the operator perspective. And we started out designing for the airline use, and it was only after we were done with that we looked at how it compared for helicopters, and then we were like, oh, wow, 24 times better. That seems important, and it turns out to be the linchpin for the same reason I think that Elon Musk's first electric car is the Tesla Roadster. Elon Musk did not build a little econobox. He didn't build an electric taxi. Elon Musk built a sports car, and he built a sports car because the electric motive power has a key advantage, which is 0 to 60 time. And for enthusiasts, that matters a lot. For taxi riders, it doesn't matter at all. So he was smart. So Elon was smart. And it turns out that we have fortunately sort of backed into the same concept, which is the R model, regardless of whether we achieve the airline or not, the R model is got lots and lots of demand and justifies the program and will make people happy and will make operators money. And so we expect it to be a very successful program. So with that, I'm going to pause and see what we have for questions.
Okay, thank you, Pete. I think Scott, do you collecting the questions for Peter?
Yep, I have a couple to get started on. One of them, I'm going to combine a few questions into one. One is, so it's really around what are the engine options you're considering, and then at what point in time does it seem like battery power would be a reasonable capability?
Okay, great question. So we started out thinking of the aircraft as a turboprop that could go vertical. We now think of it as a helicopter that can fly on a wing. And so from an engine perspective, we've explored the trade-offs with all of the major turbine engine manufacturers. We have not entered into partnership with anybody yet, so we're still working on those trades right now. But it is going to be it'll be a turbo shaft, I can say that much. And in terms of when we can electrify, so one of our partners is a company called Vertigo Aero. CEO is Eric Barch, co-founded by Eric Lindbergh, Charles Lindbergh's grandson. Eric is an electric aircraft pioneer, and they're making very cool hybrid electric systems with Continental engines, Anyway, so they know way more about this than we do. So we asked Eric that question. When could we achieve our full mission envelope with electric? And unless there's a surprise breakthrough in battery chemistry, sadly, it wouldn't be till 2040. But everybody is betting on a surprise breakthrough in battery chemistry. There's billions of dollars being directed towards that. So, we're hopeful that that'll happen much sooner.
So I have another one here on, it says Beta have quite publicly denounced the complexity of tilt rotors and tilt wings in favor of lift and cruise, citing propeller pitch adjustment. Do you find that changing the propeller or pitch is a source of great complexity for you, and how have you decided on a tilt wing?
Yeah, that's a great question. So we looked at the CL-84 and said, you know what, those guys made it work beautifully in the 1960s with mechanical mixing boxes. They had fancy little bits of curved metal to make that aircraft work. We're like, we've got computers and electric actuation. We can actuate each control surface individually, and in fact, we do in order to achieve the performance. So no, changing the pitch of the propellers is not hugely problematical. What you have to do is you have to coordinate the rates of change of all of the flight control surfaces, the wing, the propeller pitch, our trailing edge flaperons, the elevator, all of it in nonlinear ways in different flight modes. That's what's complicated. And we've spent now quite a while in simulation working that out, both with some theory-based and some pure empirical. It turns out my being an aerobatic pilot has actually been quite useful in that process because somebody who's never flown outside the normal envelope of a transport category aircraft isn't going to feel as comfortable as I do, for example, pointing the aircraft at the ground and manipulating the flight controls in the sim to see what it does. So no, I mean, lift plus cruise, in some sense, it's the simplest possible VTOL architecture, right? It's just dead simple. It's going to work, but you're carrying a lot of extra weight around and extra drag. That's the trade-off. So we've had to put a lot of work into the nonlinear dynamics of the transitions, but we had the inspiration of the CL-84 to give us confidence it can be done, and it can be done. It can be done simpler than the CL-84. For example, we're doing it without tilting the tail. We don't need to tilt the tail to control the pitch attitude, and so we don't. And so we're already a much simpler aircraft.
All right, thanks. The next one is relative to price. Is what technologies and techniques are you using to achieve the dramatic price difference from the AW609?
Oh yeah. Well, I mean, it's kind of simple. The AW609 has 2 rotor heads, and we don't have any. We have constant speed propeller hubs. Those rotor heads are cross-shafted with clutches and failover stuff for reliability in the case, so they can fly single engine briefly when there's an engine out. We don't have any of that. We have the parachute, and so if one of our propellers stopped turning, there's an impulse breakaway kind of scheme in there. Pop the parachute, you float down. One engine, again, as I mentioned, it's a huge savings in complexity because you don't have to design all that mechanical redundancy, and you don't have to teach the flight control system how to safely manage it. and it's a smaller aircraft, right? Aircraft cost tends to grow pretty linearly with size. So, you know, the VI is linearly substantially smaller. I mean, if we go back and look at the picture, you can see the 609 is about 30% longer. So all of that plays together, but I think complexity is the most important.
Mm-hmm. There's a few around really kind of airframe design, and I'll give a couple of them in a row here, but just start off with one. Why are you showing the aircraft with skids rather than wheels? Is there a performance advantage to a rolling takeoff?
So that's a philosophical question that we feel strongly about for two reasons. One is, in theory, yes, there's an advantage to a rolling takeoff. In theory, you could take off heavier, right, than you could take off vertically. In practice, if I'm going to do a rolling takeoff, I have to use an airport. If I'm going to do a rolling takeoff from an airport, there's already aircraft that do that much better than this aircraft. They're called fixed wing turboprops. So there's no point trying to compete there. And it's not our model. Our model is to compete with helicopters. Helicopters typically don't do rolling takeoffs. You know, they'll lift up and accelerate into translational lift, but they can climb straight up for a bit if they need to. So, you know, we're going after the helicopter market. It's additional features that don't give any benefit, but do add cost, weight, and certification, complexity, and risk. So, no.
So a couple of them, I'll just say, talking about noise, and both interior and exterior, relative to urban environment, along with pressurization as a comfort.
Yeah, so the aircraft will be pressurized. You know, we expect to maintain a 8,000-foot cabin altitude like a standard old school airliner. That puts the pressure differential, since we're going to certify it up to 20,000 feet. It's not very high, so it doesn't require a huge amount of work on the pressure vessel. Noise is obviously always a real concern with a rotorcraft. We've designed this so that the tip speed for the mains is about 0.5 Mach. Our aerodynamic, our noise people tell me that means they're quiet. However, the tail fan is going to be kind of like a tail rotor in a helicopter, and we know that requires careful design to keep the noise down. So that's a item we're working on now, or starting to work on now, from a noise perspective. The turbine has its own characteristic sound. So when people ask me, what you would expect this to sound like, I sort of tell them I think it'll sound like a King Air C90, right? We have about the same power, although it's in one turbine instead of two. We have two propellers, and then we got the tail fan. So our operating model so noise is an issue only if it irritates people. Okay? Noise, I mean, there are regulations. You've got to meet the regulations, yes. And we're designing to do that. And after that, it's only an issue if it irritates people. And Uber has actually done great work collating research studies around this, because it's such a huge potential drag on the urban air mobility market, which we're not in. But so we've benefited from that work. So I appreciate Uber's collating this. And there are a couple studies. One is a study up in the North Sea that said that helicopters were the most annoying noise source to people unless they were in the oil business, in which case it didn't annoy them at all. And I'm not talking just about the oil workers, I'm talking about their families and people.
Yeah.
There was another good study about community involvement. They expanded SeaTac Airport. New airport manager went around in advance and got input from everybody. And the equivalent annoyance level, they dropped it by 20 dB. So it was 20 dB less. And that's a huge lesson. So one of the things we've done in terms of our outreach is we're already talking to city planners and regulators and mayor's offices and community organizations and starting to get their input. A key enabler of the VIP aircraft will be the airline strategically, because the airline is actually going to give you cheaper door-to-door costs than existing Uber to the airport, airline ticket, Uber to your office, your destination. So it's going to be for everybody. Our model is for well-off people. The airline's for everybody. And so that's going to give us a big constituency who won't mind it. Last thing is, I think landing on rooftops is a dumb idea. I don't support it. And our operating model for the airline doesn't use it. We tend to operate off waterfronts or adjacent to industrial land where we can have the noise when we're down low, not over buildings, not over apartment buildings, not over offices. So noise, like safety, is an emergent property of a system level set of choices you make. It's not just about having an electric motor instead of a turbine. That's kind of the least important part of it.
Good. I have a question on the business model side of things. And what is the impact of COVID-19 relative to how your business model is laid out?
Yeah, so we're not sure. Obviously, we're in an era of huge uncertainty. But I think the rebound in the business jet market is starting to look like a V instead of a U. In other words, it's coming back pretty quickly. The business jet press is reporting new customers. So people who've decided that in the era of COVID, having the room and the privacy of a private flying experience is important. So, you know, those we look at as positive signs for our business model, that more people will be interested in buying the aircraft, more people will be interested in an airline experience where you're sitting 6 feet away from people. So to the extent that holds on, that should be positive for us. You know, it is a drag right now as we're going around and partnering, because it's hit the industry partners we're talking to very hard. And so, you know, that is what it is. But fortunately, we're organized to be able to continue in the face of it, so we are.
Scott, how about one more question?
Yeah, one more question around the safety of the parachute, particularly at low altitudes, and what sorts of certification testing has to be done for that?
Yeah, that's a very good question. So the VI will have an HV envelope just like any helicopter does, right? You know, helicopters are relying on auto rotating, and you know, you have to be outside the avoid areas to successfully pull that off. So like I said, at low altitudes, you know, kind of the 30 to 50 foot level, Part 27 crashworthiness is what provides the safety. And not just, you know, we plan to go beyond that with frangible structures to absorb impact loads. The takeoff, once you have forward motion, which we can get, this aircraft accelerates very quickly. So, you know, our takeoffs will look kind of like a traditional helicopter takeoff, where we, you know, hover taxi out over the FADO and then accelerate at low altitude before we zoom up. And in that zoom, we're already, you know, we get to 100 knots in seconds. So at that point, the parachute starts significantly reducing impact loads, even at as little as 100 feet. It's not going to be fully inflated, but it helps substantially, and it gives you a predictable orientation of the aircraft on impact. So we're working with BRS to design the crumple zones effectively in the aircraft, that knowing that, we can demonstrate to the regulators that these will be survivable impacts. And of course, there's going to be interior you know, seat belts. We'll have 3-point seat belts with airbags in all likelihood, and other things. But again, you know, safety is a system property. So we're designing the entire aircraft together to deliver on this. It's not just a parachute or auto rotation.
Very good, thank you.
Yeah, great, Peter. I can't thank you enough. What a great presentation, fascinating product, and I wish you all the best in your endeavor, and really, really appreciate you taking the time to talk to our little East New England chapter, and as well as folks who are actually tuned in from all over the world. So thank you.
Well, it's been an honor to be asked. Thank you very much for having me, and glad to have gotten to share. So,
great, and again, thank you to FLIR Systems for sponsoring this webinar. And you know, we'll be taking the summer off because a lot of people go on vacation. So typically our attendance in summer session meetings is pretty low. So we'll be back again in September. So stay tuned for our announcements on who will be our guest speakers. So again, thanks again to the Vertical Flight Society headquarters for letting us use the software, and to Peter for making just a terrific presentation. Thanks, everybody.